Okay, folks, time for lecture number 25. Can folks in the back hear okay? Yeah? No? Yes. Okay. Announcements. There will be a Gorilla section this weekend on how to use Scheme and functional programming languages in general. Those are important concepts like linked lists and higher order functions and recursion. We've been looking through these for the whole course. Scheme really pushes you to use them. If you want more practice, come to the Gorilla section. It will be on Sunday at 12:30 in the Soda Hall Labs, 271. Remember, Gorilla sections are a chance for you to really master this material deeply. It's a very good chance to see the kinds of problems that show up on exams and homeworks and to work on them with a group of people. Homework 7 will be posted after lecture, and it's due next Wednesday. After that, there will be a quiz. And the quiz is on Scheme. The homework's on Scheme. So it's time to learn the Scheme language. Any questions about that? What? Oh, is the date wrong? Oh, November 5th. Yeah, you have a while to solve homework 7, apparently. It's due next Wednesday. Sorry. April Fool. Project 1, 2, and 3 composition scores can be raised up to 100%. All you have to do is revise your projects based on the suggestions that were made to you by the course staff. So please do that. Almost all comments for Project 3, I think, have been distributed. We'll finish that up in the next day. There's a new policy I announced last time. If you go to lab, then you can skip the final exam. Okay, no, that's not true. April Fool again, for real this time. Okay, so if you go to lab, you can earn back up to 5 points that you lost on midterm 2. Some conditions apply. This only applies if you got a 35 or less. But please go to lab. It's a great chance to get familiar with the new concepts like the Scheme language. Hopefully you went this week. And the following labs will help make sure that you're ready to work on Project 4, which is coming up, and it's the largest project in the course. Every project is the largest project. That's true. They just keep getting bigger. April no fool. Okay. Any questions? Okay, the last lecture I told you about the Scheme language. Today's lecture is mostly back about Python, but there's one demo on Scheme that I kind of like, but I didn't have time for last time, so I'm just going to squeeze it in right now. Show you an example of the things you can do with a programming language that you learned in just 1 hour. Okay, so I'll start up Scheme. The version of Scheme that we're using in this course has a built-in drawing package called Turtle Graphics. And what it does is it allows you to control this turtle, which looks like an arrow. And here I've told it to go forward 100. I can also say, please take a 90-degree right turn. You see it turned. And if I tell it to go forward 100 again, then it'll go forward 100 again. Oh, let's make another right turn. Oh, let's go forward 100 again. And I've almost built a box. Now that's cool, but not that cool, because we haven't really written an interesting program yet that allows us to repeat or otherwise structurally create an interesting image. So let's do that. Let's define a procedure called repeat. And repeat will take in an integer k of how many times I want to repeatedly call some function. Now, if it's the case that k equals 1, all I'm going to do is call that function. The way you call a function in Scheme is you don't put parentheses after it, you put parentheses around it. Here I'm calling the function fun with no arguments. If k is larger than 1, then what do? Well, I call fun, and then I repeatedly call fun k minus 1 times. Now you can't actually just have two expressions in a row like this. If you want to have two expressions in a row and just evaluate them all, there's a special form called begin that does that. So begin just says, do the first thing and then the second thing. So call fn, and then repeat calling fn k minus 1 times. This is a recursive function that just calls fn k times. So we'll start up scheme again, and here we're going to repeat 5 times the following function. A function that takes no arguments, goes forward 100, and then takes a right turn of 144 degrees. That's the end of my lambda procedure. That's the end of repeat. Now I let it run. Oh, it got really mad because I forgot to load this file. Let's try that again. We'll let it run, and it will repeat that process over and over again. So let's say I wanted to define a triangle. Well, a triangle is what you get when you take in some function for how to draw one of the legs, like for instance just the function that draws a line, and you do that 3 times in a row. So I'll repeat 3 times, where what I'm going to do is call this function that draws a leg, and then I'm going to take a left turn of 120 degrees. Okay, so we'll load this version, and then we'll draw a triangle where all I'm going to do for each leg is move forward 100. Okay, not that impressive a demo. But there's this thing called Sierpinski's triangle. Anyone ever heard of it? Yeah, okay, Sierpinski's triangle is a triangle where the legs aren't just lines. Instead, the legs are Sierpinski triangles. So a Sierpinski triangle is formed of 3 Sierpinski triangles, one for each leg. We can define that, no problem. So here's how we'd write that in scheme. We would define Sierpinski's triangle of some length d and some depth k as follows. 3 times in a row, I'm going to check and see if it's the case that k equals 1. That's a base case, in which case I'll just draw a line, forward d. Otherwise, I'll draw a leg of Sierpinski's triangle. Now, what is the leg of a Sierpinski's triangle? Well, I just told you. It's a Sierpinski triangle. So here I make a recursive call. The thing about Sierpinski's triangle is that the 3 triangles that form it are all only half the leg length of the original triangle. So here I divide d by 2. I subtract 1 from k so that one day I'll reach the base case. And then, in order to make sure everything lines up, I have to pick up my pen, I have to move forward d, and then I have to put my pen back down. Those are all drawing commands, and I'll explain what they do as we watch the turtle draw Sierpinski's triangle of length 400 and depth 6. Okay, so what's going on? It's drawing actually a big triangle, but the way that it does it is it draws 3 smaller triangles. Each one of those is 3 smaller triangles, and each one of those is 3 smaller triangles. When it finishes drawing the leg of one of these smaller triangles, it moves into position to draw yet another leg. And so here we're about to draw the 3rd leg of this Sierpinski triangle here, which is really just made up of base cases where you draw a triangle by moving forward some length d. Now once it finishes drawing that, it's going to start drawing another Sierpinski triangle here, and eventually it'll get around to drawing another Sierpinski triangle over there. Question? Oh, someone's bored and they want to speed it up. Okay, sure. So we gotta just stop doing that. Cut it out, turtle. You're so boring. Let's get some speed. counterintuitively, speed 0 is really fast. I think we need to make it a little bit smaller so it fits on the screen. Okay, now it's going crazy. Are there other questions while I show you the code and the output? Uh-huh. So the question is, could I have defined this whole sire thing in one function instead of breaking it up into sire and leg? I could have put it all together. I was just trying to break it up into two pieces so it's a little bit easier to digest. Oh, so the question is, how come I'm allowed to have a bunch of different expressions, pen up, FD, and pen down all together? Well, it's not the fact that they're on the same line. I could put them however I want, and I can space things crazily in Scheme, and nothing will break. But what is going on is that the body of a define, or the body of a lambda, can actually take multiple expressions. And Scheme just evaluates them in order, and then the value of the last expression in the body is the value of the call. So the reason I had to write begin is that I was in the middle of some other expression, in the middle of an if, I think, in this case. Where did I write it? Oh yeah, so in the middle of an if. And that position only takes one expression, not a bunch. So if I ever want a bunch where I'm only allowed to have one, I have to use begin. And begin is one of the things that you'll learn about as you work through your project, because you have to implement how it works. Question in the back. So does memoization help us here? It actually doesn't, and the reason is that there is some state. There is some mutation that's happening with each one of these function calls. So these are not pure functions. And that state is actually that the turtle is moving. So drawing the first leg is different in a way than drawing the second leg because the starting position of the turtle is different. So memoization only works with pure functions where you're actually doing exactly the same thing over and over again. Okay, enough of that. Let's learn some Python. Today we're going to talk about exceptions. Exceptions are a mechanism to handle errors. And the way in which you handle errors in a program is an important part of building some application. It would be nice if everything we built just did what we wanted it to do, and every user that ever used it did exactly what we expected them to do. But that's not the reality of programming. So we need to think about exceptional circumstances when things go wrong and how our program should behave in those cases. So today's topic is the handling of errors. Sometimes computer programs behave in non-standard ways. Because a function maybe receives an argument value of an improper type. What do you do? For most of this course, we've just been assuming that will never happen. But it really does happen, and you have to start thinking about it. Sometimes you try to do something like open up a file, and that file's not there. Sometimes you try to communicate with another computer over a network, and something's wrong, because AirBears is giving you a hard time. This is a page out of the notebook by Grace Hopper, one of the foundational computer scientists in our field. And she was working on a very early computer in 1947, and her computer shut down. She finally figured out why, because there was a moth that flew into relay panel number F, and so she wrote in her notebook, this is the first actual case of a bug being found in a computer program. Okay, so things will go wrong, and we have to build systems that are robust to that. Now, so the terminology of a bug already existed, and then this was already funny back in 1947. But this joke never gets old, in my opinion. Okay, so exceptions are the concept which has associated syntax and objects in the programming language for handling errors. So error is just something that we talk about among people. Exceptions are a thing that's part of the programming language. It's a built-in mechanism in this case that lets you declare that an error has occurred or respond to some error that's occurred already. So Python raises an exception whenever an error occurs, and that's already built in to the way that Python interprets a program. Exceptions can be handled by the program, which will actually prevent the interpreter from halting. So kind of the default behavior when an error occurs is that program execution halts, and you get a display so that you, the programmer, can see where the error occurred and what happened. The program doesn't just keep trying to compute even though you divided by 0 somewhere. It stops and says, something went wrong, figure it out. And that's a fine behavior for an interpreter of a programming language, because you want to get feedback as early as possible when something in your program is going wrong. That's actually not the ideal behavior if you're building a service for non-programmers, people out there in the world who are using Google Search or Facebook or something like that. They don't want to see a stack trace every time Facebook divides by 0. Instead, they'd like the system to just keep running. So there are certain applications where it makes sense to just halt the computation and show people an error report, but there are other situations where it would be much more helpful if the computer program just kept running. Just accepted, oh, something went wrong, but I have some backup plan B, and I'll do that instead. So unhandled exceptions will cause Python to halt execution and print a stack trace. But if we handle them, then we could prevent the interpreter from halting and instead do something else instead. Oh, instead. Okay. So I'm going to go through a bunch of examples of how all this works, but here are some things to keep in mind if you want to really master this concept of exceptions. 1, an exception is an object. That means it has attributes, it has a class, it can be built with a constructor. It's a thing just like any other object in our system. And the powerful thing about exceptions, the things that make them different from everything else that we've experienced so far, is that they let us have non-local continuations of control. So what's control? Control tells you what to do next in a program. Normally you go down line by line, but an if statement is a form of control. It says either you do this or not. A while statement is a form of control. It tells you to repeat a certain block of code. Well, a return statement is a form of control that tells you to stop executing the body of one function and return back to where you were in another function, the function that called you in the first place. That's a local continuation of control because you always jump back to the function you were in before. Exceptions actually let you jump back into a completely different part of the program. That's non-local continuation of control. So here's the image to keep in your mind. Exceptions allow you to do the following. If F calls G and G calls H, normally H would return to G and G would return to F. But exceptions let you skip that process. You could have F call G and G call H, and H raises an exception, and it gets handled in F, and G just gets ignored. That's what exceptions allow you to do. Okay, so I know that's abstract. Let's go into the details. Unless questions already. Also, exception handling tends to be slow. So you use it for exceptional circumstances. It shouldn't be the case that all your program does in every case is raise an exception. Instead, that should only happen when something's going wrong. Okay, so exceptions can be raised. How do you do that? Well, the simplest way, and the way that we've been using in the course already, is with an assert statement. An assert statement raises an exception, and that exception has a type. The type is called assertion error. How do you raise an assertion error? Well, your assert statement says, assert some expression. That expression gets evaluated. If it's evaluated to a false value, then an assertion error is raised with this string here, as an attribute that tells you what went wrong. But assert statements don't always have to work. Assertions are designed to be used liberally, meaning you put them all over your program, just to make sure your program is running as expected. But if you ever get to the point where you wish these assertion errors weren't always running because they took too long to run, you can turn them all off at once by starting Python with -O. O stands for optimize. So if I run my program like this, then assert statements don't do anything anymore. And whether assertions are enabled is governed by a Boolean value called debug with underscores around it. Okay, I'm tired of talking. Time to write some code. Goodbye, Sierpinski's triangle. Goodbye, scheme. Hello, Python. If I assert false, disaster, I see an error. Oh, assertion error. Disaster occurred. And this is the same thing if I have an expression that evaluates to a false value. So if 2 equals 1, disaster. If I put in a true value here, nothing happens at all. If I restart Python with -O, at this point, debug is false, and if I assert 2 equals 1 disaster, then what happens? Nothing. Okay, I mostly showed you this example to notice that exceptions have been something you've been experiencing all along through this course. Here's one way to get them. And this thing here, this last line of the stack trace that you see, tells you the class of the error that happened, and then some message that's an attribute of that error. Okay, questions so far? Fine with me? Assertion errors are not the only kind of errors. You can also raise any kind of exception you want using a raise statement. This is a new piece of syntax in the language that we haven't seen before. Exceptions are generally raised with a raise statement where you just say raise, and then you write some expression. That expression evaluates to an exception, which is an object. So expression must evaluate to a subclass of the base exception class, or an instance of one of those. So base exception is an exception, and everything that inherits from it is also an exception. And exceptions are constructed just like any other object. So you'd say something like, oh, I want to raise a type error where my message is bad argument. And that will create a type error exception and raise it. Now what does raising it mean? Well, it means you stop executing the function that you're in right now, and you show an exceptional output, an error report to the user, unless the thing gets handled, which we haven't talked about yet. Okay, so what is a type error anyway? Well, each class of exception is associated with a certain kind of thing that can go wrong. And this allows us to have some structure over the space of all errors that may occur. So a type error is used when a function was passed the wrong number or type of argument. A name error is used when you try to find a name somewhere in the environment and it's not found. A key error is raised when you look in a dictionary for a key and you don't find it. And a runtime error is some catch-all for any trouble that happens during interpretation. So anything that just breaks unexpectedly, that's a runtime error. Okay, let's raise all of these errors. So I want to raise a type error. Disaster. Here we see an error report where it says that a type error was raised and its message was disaster, or wrong type type of argument, would be a more typical error. And this is the same kind of error that you get when you try to take the absolute value of a string. It says type error, bad argument type for abs, str. You can ask questions if you want. Otherwise, okay. Yeah, so if I said something like if 1 equals does not equal 2, 1 does not equal 2, then I might want to raise an error. That's basically equivalent to asserting 1 equals 2. So that kind of polarity of the expression changes, but otherwise you get the same behavior. But exceptions don't get turned off when you go into optimized mode of Python, only assertions. Okay. I told you I'd show you all these different types of errors. We saw a type error. Maybe we could have a name error. Hello. Oh, name error. Name hello is not defined. That's very rude. What else? Let's have a dictionary here. This dictionary, does it have a key called hello? No. Key error. There's no hello. What if I define the following function? Is that bad to do? Oh, apparently it is. Runtime error, maximum recursion depth exceeded. Why did I reach a maximum recursion depth? Oh, I defined a function that just called itself over and over and over again. That would run forever, except for that there's a mechanism in Python to stop functions from calling themselves too many times. It has a maximum recursion depth. Oh, what is that depth? It changes depending on the version of Python. I think it's like 200 on my version of Python right now. Yeah, so it's unreliable. You can actually set it. I'll let you look it up. Okay, so there are some different kinds of errors that you may encounter. Now, I talked about raising errors. That means declaring that something bad happened. I also need a mechanism to handle the fact that something bad happens. And that's called a try statement. So a try statement is our mechanism for handling exceptions. And it has a complicated syntax. It's a compound statement that starts out with the word try all by itself. And then there's a try suite that can contain any piece of code you want. It's just saying, first try to do this. Now there's some structure to the rest of the clauses. There's an except clause, which has to declare a class of exception that it's going to handle, and then the name of the exception that gets handled, so that you can refer to the exception itself. So remember, an exception is just an object. You construct it just like you'd construct any other object, and here we can give a name to it and inspect it, do things with it, just like any other object. And that's what the except suite is for. Here's the execution rule for a try statement. First, try to execute the try suite. If it's the case that during the course of executing the try suite, an exception is raised that is not otherwise handled, and it's the case that the class of the exception that was raised inherits from the exception class. The exception class is here. Then the except suite is executed with name bound to the exception, and the exception is considered handled, meaning you won't see an error report. Instead, the program will keep on running. Okay, so that's the abstract description of exactly what this thing does. Can we see it in action? Let's look at some examples. Here's how you handle an exception. So the point of exception handling is you can prevent a program from terminating. Instead, you can say, please keep going under the following conditions. And you do that by saying, try, and then you can put anything you want there. Here, we have x equals 1 divided by 0, which will raise a zero division error. But fortunately, I've written an except clause where I've said if it's the case that the try suite raises a zero division error, I will call that error E, and I will print out I'm handling an error of type E. Here I've actually said, if I ran into this zero division error, I'd like to give x a value of 0. Now, didn't x already have a value? Well, no, because we were trying to execute x equals 1 divided by 0, this assignment statement. But how do you execute an assignment statement? Well, you have to figure out what to assign x to first, and that means dividing 1 by 0, which caused an exception. So we never got to the point where we bound x to anything at all. But in this structure, no matter what, x will be bound to some number. Because here we say x equals 0 in the case that we accidentally divided by 0. Okay, so if I run this, it will say handling a zero division error. That's the type of E. E is an exception. And if I look up what x is at this point, it's 0. And it's 0 because we set x equal to 0 right here in the except clause. And then it will keep on running the whole program as if x were 0, because x really will be 0. Exactly. In the back. Okay, so this try and raise business is always on. And they can show up anywhere in your program. So in the middle of a function that you've written inside of another function, you can say, I'm worried that I might accidentally divide by 0, so instead of just computing something, y divided by x, I'm going to try to compute y divided by x and accept the case that a zero division error occurs, at which point I'll return some special value like 0. I'll show you an example. But first, I just want to, for completeness, you can have lots of these in your code anywhere they want. What happens if you have multiple different try statements? Well, here's a detail that you have to know, which is that the except clause that you jump to is the one from the most recent try statement that handles that type of exception. So if there are multiple different try statements that accept zero division errors, it will pick the one that you most recently executed. Okay. Yikes. So, let's define a function. Invert takes in x, computes 1 divided by x, prints never will be printed if x is 0, returns the result. What does this do? Well, I can invert 3, and it will print never will be printed if x is 0, and then it will return 1 divided by 3. Or I could put 0.5, and it will invert it to 2. And what happens when I invert 0? Well, I get a zero division error. from line 2 of x.py, which is this file over here. I divided 1 by 0. And by the way, this was never printed because x was 0. What if I don't want these errors? Well, then I could come up with a safe version of invert, which would try to return the inverse of x. But if for some reason that doesn't work out, like for instance, if someone decides to divide by 0 somewhere within this call to invert, then I'm going to handle that exception and instead just return a string representation of E. What's E? What's the exception that was raised? So it's still the case that if I invert 3, I get 1/3. If I invert 0, then I get this error. What happens if I invert safe 1/3? Exactly the same thing. Invert safe calls invert. Invert returns 1/3. 1/3 gets returned from invert safe. Nothing ever happened down here because nothing ever divided by 0. But if I do divide by 0, then I don't see an error report. All I see is the string division by 0. Why is that? Well, what happened is I inverted 0, which attempted to divide 1 by 0. I never printed this. Instead, I immediately transferred control to this line, which is the first line of the clause within this try statement that handles 0 division error. Okay, so we divided by 0 and the computer didn't break. Because it's up to us exactly what happens when an error occurs. And the way it's up to us is we add try statements to our code in order to handle these exceptional circumstances. Question? Oh, if I got rid of this, and I just said print hello, or anything. Or I said y equals 27. Let's invert safe 0. All it does is print hello. So we called invert safe, which called invert, which divided by 0, never got to here, because as soon as you divide by 0, you jump back to the most recent except clause of any try statement that handles that kind of error, and you execute its suite, which printed hello. And then set y equals to 27, which is totally useless, and then it was done. So the question is, why would we ever have a try statement when I could have just protected against dividing by 0 within invert? This is a separation of concerns. You can write the functionality for how something's supposed to work when nothing wrong happens in one place, and you can write the try except behavior in an entirely different place. And this is very common when you write a large program and you're using some library that somebody else wrote where they didn't know what kind of application you were writing. So they didn't know whether you wanted to print out a whole error message, or whether you wanted to try a second time, or whether you wanted to just keep on going. So it's up to you to decide how to do that in a try statement where you call a function from that library, and then you say what happens when something goes wrong. What? Oh, you can put any name you want instead of E. E is a pretty good name for an error. All right, ready to do some work? What would Python do? What would Python do? So here's the same thing I had before. Invert computes the inverse, 1 divided by x. There's this never printed business, then it returns the inverse. Invert safe returns invert of x. If there's a 0 division error, then it returns some string like division by 0. What happens if I invert safe 1 divided by 0? Talk to the person next to you, see if you can figure it out. Alright, let's return this to its former glory. We know that invert safe of 0 just writes division by 0. What about 1 divided by 0? We get a 0 division error. I thought we were handling 0 division error. Well, we're not handling this 0 division error. And the reason is that the way this expression gets evaluated is it looks up what invert safe is. That's that. It looks up computes what 1 divided by 0 is. Oh, that's an error already. It never actually called invert safe, which means it never actually executed this try statement. The error had occurred before it ever got that far. So try statements only handle exceptions that occur while evaluating something within this try suite. If they happen outside of that, then you're in trouble. Questions about that? In order to handle this exception, we have to have a try way out here. Whoops. Oh, man. Oh, no, I did it again. April Fools. Okay. That was a lot of typing just to show you a very simple example, but good question. Okay, how about if I try invert safe 0, accept 0 division error, print handled? What happens there? Okay, what are our options? It could print handled. It could divide by 0. It could raise an error. It could just actually compute 0. Talk to the person next to you, see if you can figure it out. Okay, try invert safe 0 is going to try to invert 0, which is going to divide by 0, accept 0 division error as E, print handled. We'll print division by 0. That came from this return statement. Even though 0 division error occurred, it was handled here, at which point we're returning back to normal execution. this error is already handled. And all this invert save function does is return the string division by 0, which is not a 0 division error. It's just a string. This could be anything. And it would just print out that anything. And so it never gets to this print handled part. Question? Okay, one more. Oh yeah, question. We're in an interactive session here, right? The triple carets. And when I write try, I'm not actually creating a new function. It's just like writing if. So I'm not returning because I'm not inside of a function to return from. Good question. So here's a function, so I return from it. This out here isn't a function. You can't put a return out here. What's that? You can, an exception is just an object. You could return the exception object and do anything you want with it. Usually you return a more useful object, like a number or a string or something like that. How about invert safe, 1 divided by 0? Talk to the person next to you. Figure it out. Invert safe, 1 divided by 0. Division error? No. Name error. Okay, the order of operations is important. First thing, you figure out what invert safe is. Well, it's nothing. And then you would divide 1 divided by 0, but we never even got that far. So the first exception that gets raised will halt execution of whatever statement you're in the middle of and go shift control to any except statement that handles it. Since we don't have anything that handles a name error here, we see an error report. Okay, see you Friday.